This video is on binary search tree. Here's a roadmap of what we will cover. In this video, we will cover the delete method of binary search trees. As we do that, we will also conduct its time complexity analysis. Let's get started. To make sure that we are on the same page, some clarifications first. First, we have set up the implementation of the node class to represent each node in a binary search tree. Each node has a value and two references leading to two different other nodes, the left and the right children. For simplicity, a node only deals with integers. Second, based on the implementation of the node class, we have also set up the skeleton of the class representing a binary search tree, and there's search, insert, and delete methods. We implemented the search and insert methods in the two prior videos, and the delete method is what we are going to implement in this one. Third, imagine that we already have a binary search tree example that looks like this on the left side of the screen. With these three assumptions set, we are ready to discuss the delete method. The delete method deletes a node based on a given target value. However, it is more complex than the search or the insert methods, because there are different cases. Actually, there are three different cases in deleting a node. The first case is when the target node is a leaf node. The second case is when the target node has a single child. The third case is when a node has two children. Let's go over the cases one after another. The first case. If the target node is a leaf node, we can simply delete the node by setting its parent's corresponding reference to none. For example, if we were to delete this target node with a value of 36, it's a leaf node. We can simply achieve our goal by setting the reference of its parent node 34 to none. Is node 36 still there? Yes, for a while before it's automatically cleaned as a garbage. So case 1 is relatively simple. All leaf nodes can be deleted in this way. The case 2 of the delete method is when the target node has only one child. In that case, what you do to delete that node is to replace the node with its only child. And you do so by adjusting the reference of the target node's parent. For example, if the target node that we want to delete from this binary search tree on your left side is the node 34, then you have a case 2, because 34 node only has a single child, which is 36. How do we do it? We will adjust the reference of the parent node of the target node. The parent node of 34 is node 32, and node 34 is the right child of 32. So we adjust the reference of 32. By saying that, I mean the dot right reference of 32, so that it points to 36, like this. Is the target node 34 still out there somewhere? Yes, for a while before it's collected as a garbage. That's how you deal with a target node that falls into the case 2. What about case 3? Case 3 is the most complex one in comparison. When the target node to delete has two children, you have a case 3. How do you do it? First, you will find a replacement value. Where does that value come from? Either the smallest node in its right subtree or the largest node in its left subtree. We have names for the two nodes where the value may come from. The smallest node in its right subtree is called the in-order successor. The largest node in its left subtree is called the in-order predecessor. Second, you will copy its value to the target node. Third, you will delete either the in-order successor or the in-order predecessor, depending on which node you used its value. Let's use an example to demonstrate how case 3 works. For example, the target node to delete in this binary search tree is node 66. This node has two children, so it's a case 3. Following these steps, The first thing that we do to get the value from its in-order successor or predecessor. For example, its in-order successor is the node 75. The node 75 is the smallest node in the right subtree. To find the in-order successor of a target node in a binary search tree, you will start by moving to its right subtree first. After that, you will repeatedly follow the left child of each node until you reach a node with no left child. That node is the in-order successor. Similarly, if your goal is to get the value of the in-order predecessor, you need to move into the left subtree of the target node first. After that, you will repeatedly follow the right child of each node until you reach a node with no right child. Then that node will be your in-order predecessor. In our example, the in-order predecessor is the node 65. Okay, that's step 1. Let's stick to using the in-order successor. In step 2, you will copy its value to the target node, like this. After that, you will go to step 3, which asks you to delete the in-order successor. In our example, that's the node of 75. Since node 75 is a leaf node, deleting it will be actually the case 1. In other words, all you need to do is to set the reference of the parent node of node 75 to null. So we will set the dot left of node 80 to null, like this. That's one example of how case 3 works. To make sure we are on the same page, let's try another example. In this example, the target node to delete is node 31. First, we need to find the value that will be used to override that of the target node. If you want to use the in-order predecessor, then we need to navigate into the left subtree. Since there's one node, and only one node in the left subtree, that's our in-order predecessor then. That's node 20. However, if you want to use the in-order successor instead, you need to navigate to its right subtree and keep following the left child of each node until you get to a node with no left child. The in-order successor is node of 32. If you were to use the value to replace that of the target node, it will look like this. After that, we will move to delete the in-order successor. This is a case 2 of deletion. In other words, we will need to adjust its parent node's reference. The parent of node 32 is node 41. Node 32 is the left child of node 41, and node 32 only has a single child, which is the node 34. So we will adjust the left child reference of node 41 to node 34, like this. Now you have completed the deletion of the node 32. These are the 2 examples of how the steps of the case 3 are carried out. Translating these steps of all cases to pseudocode, you will have this. As you can see, we are doing some overloading here in the pseudocode, just like how we dealt with the search and the insert methods. The 2 functions come with the same name but different parameters. The first function is the one that's exposed to users, while the second one is hidden from the users but does the heavy lifting behind the scene. This setup is user-friendly and makes it easy for the implementation. Let's focus our attention on the second function since it does the actual work. This function always returns a node to maintain the proper tree structure. If the current node is not null, then it will start the process of searching for a node with the given target value. It does so by comparing the target node's value to the target, and then navigate to the left or right. When the target node is found, it will start dealing with the 3 different cases we just covered. When translating the steps to pseudocode, we don't differentiate between case 1 and 2. The if and else if statements are for the scenarios when node.left is null or when node.right is null. If you want to separate case 1 from case 2, you actually can, like this. All it takes is to add a if statement at the top, then you have if, else if, and else if. But that's not really necessary if you want a more succinct version of the pseudocode. These are the lines that deal with a case 3. We rely on the help from a helper method named the main value to get the value of the in-order successor. After that, we replace the target node's value. In the end, we recursively call the delete method on the in-order successor. The last line will return the current node. It works its magic for both case 3 and when the target node is not found in the tree structure. The main value method looks like this. In the delete function, the main value was called on the right subtree of the target node, in case if you didn't notice. Like this. Now you know everything about the delete method. Let's talk about its time complexity. We will start with the worst case scenario. What gives you a worst case? When you need to traverse every node in a binary search tree to delete the target node, like this example that you see on your left, then you have a worst case. The time complexity for the worst case will be big O of n, where n represents the size of the binary search tree. What about the best case scenario? If you don't account for the time it takes to search for the target node, the delete process is typically fast enough to be big O of 1, like this example that you see here on the left. Otherwise, you will need some special example to reduce the time it takes to search for the target node to a constant amount of time, like this example that you see here. The major cost of deleting a target node is all about searching for that particular node first. Adding both the search and the delete time together, it takes constant amount of time to delete the target node, like what you see here on the left. Let's talk about the average case. The average case analysis of the delete method is the same as that of the search and insert methods. In short, the time complexity Tn is in proportion to the comparison numbers. To account for randomness, we need the help from the expected value. The assumption of computing the expected value is the same as that of a successful search. Based on the assumption, we will be able to compute the recurrence relation for the expected comparison numbers. It looks exactly the same as the average case for the search method, because the main cost comes from searching for the target node, and the delete operation has only a slight additional overhead, but can safely be ignored. On the right side of the equation, 1 is the number of comparison required at the root level, and the summation is the expected number of comparison in the next step. I divided by n multiplied by C of I represents the expected number of comparisons when the delete goes into the left subtree, while the other item represents the expected number of comparisons when the delete goes into the right subtree. With the recurrence relation, we can deduce the formula of C of n independent from the random variable I. Again, the deduction process is the same as that of the search method. It involves using the assumption of a balanced tree and what you learned from calculus, such as differential equation and how to exponentiate both sides of a formula. We will be able to deduce that the expected comparison number is log n, because the time complexity is in proportion to the comparison number, so it runs on log n time. That's the average case for the delete method. Now you understand everything about the delete method. In the next video, we'll dive into the different types of traversal on a given binary search tree.